So kind of the first concept in physics is to describe motion. It's very natural because we move all the time. One of the first things we learn how to do. Um, so, so let's talk about how you describe motion. The first step of almost any physics problem is to draw a picture, right? So let's talk about the motion of a car. So let's draw a car. Oh, how do you draw a car? Well, I've got all these colors and tools, but I'm just going to do what I always do, which is draw a terrible box. Oh no, that's even worse than usual. Okay, sure, that's a car. Where is that car? Well, I don't know. I need a reference point. Okay, so this is why we come up with axes. So I actually do have a ruler, which is fabulous. So I could say, all right, there's an axis, and there's another axis. So these are our x and y axes. So I could say, here's x, and here's y. Maybe I need some tick marks on there, right? So we could go right here and here and here. This is better than usual. I don't usually use a ruler. All right, sure, yeah, and I could use that same ruler vertically to make some tick marks. I think I missed the first one, but that's fine. It doesn't really matter all that much. Okay, great. So x and y axes. Now I can talk about where that car is, right? I could assign some x and y to it. In fact, I could call them x1 and y1. Great. Now I can talk about position. So we could even put that over here. Say position. Usually use x. If we're in just in one dimension, we'll just use x. If we're in two, we'll use x and y. If we're in three, we use x, y, and z. We won't need three dimensions until we get to physics 2. Because every motion that we'll talk about can be described in a plane, if that makes sense. And you'll think you'll see as we go. So there's position. The SI unit for this is a meter. Position is actually a vector. Position is a vector, meaning it has direction and magnitude, right? Magnitude and direction. So we could talk about the position of this car relative to the origin, right? There's my 0, 0 point. The next thing I can talk about is displacement. Displacement is it's a distance from one point to another point. All right, so I could say my car. Let's say the car moves, here, and changes shape for some reason. We could call this x2, y2. All right, so now the line that connects the original point to the final point, that's a displacement. All right, and we call that displacement delta x. Delta is a Greek capital letter. It just means change in. Let's use a different color and call that change in. Right, again, it's a delta, a capital delta. And if we were going to, come on, I really want to move. That's fine. Delta x is x final minus x initial. Almost every time, I would say 90%, 95% of the time that we use a delta, we mean final minus initial. All right, and that's what governed the direction of this. So this is my delta x. Really, it's delta x and y, so it's like a delta r, r vector. Clearly, displacement has direction, so displacement is also a vector. All right, something else. These cars are cumbersome, right? And I don't lose any information if I describe the car or truck or whatever in the world this is as a point. We call that the point mass approximation. All right, and we're going to treat objects like points until treating them like points doesn't work anymore. Specifically, when you start to think about rotation, rotation of a point doesn't make any sense. But the car here, I could say the center of mass of the car, or I could pick a specific point on the car, like the front or the back. Here I seem to have picked the cab. So I could just call these points. Oh man, this is magical. Right? So here's my initial point. Oh, no. Here, there. There's my initial point. There's my final point. In fact, I could move this a little bit. There. Right? And often, instead of 1 and 2, although there's nothing wrong with 1 and 2, we'll use initial, which I can make initial here, and final. It's harder to make 2's into finals, but Steve Jobs took care of that for me. Okay. Initial and final. Great. So there's our displacement vector. That's awesome. What else can we do? Well, we could ask, how long did it take? Right? That would be like a delta t. So we could say duration is a delta t. Right? So if I put this together, how long did it take? How far did I go in how long? I can get a velocity. For velocity, we use a v. And velocity is displacement divided by how long that took. This is technically an average velocity, and we'll talk about that in a little bit. So delta x over delta t. And if I use this final minus initial idea, I could get this as x final minus x initial divided by t final minus t initial. Often we leave the delta as a delta, the duration, the time as a delta t. But x final minus x initial is useful for a specific reason that we'll see in a little bit. Velocity is also a vector because you see it's defined using a vector. Do you see displacement is a vector, right? Let me just put that over here. Displacement is a vector. So velocity, because it's defined in terms of a vector, is also a vector. There are some vector operations that make the vectors not vectors anymore, but that's a little beside the point right now. So velocity is a vector, has direction, and clearly if we look at this, the car started here and ended here. So the velocity vector, often I like to use red as velocity. So the velocity vector points this way. That's v. Often, I like to make my v's with a little thing on it. Often for vector, I'll put an arrow over top. The arrow just means it's a vector. You could make that a full arrow. I'm just lazy. So velocity and displacement point in the same direction. Okay, great. Let's do an example. What kind of example? Well, now that we can draw a picture, let's talk about how could we draw a picture to describe not just 2 points of motion, but like the motion between 2 points of motion. Let me explain. Here. So the following motions construct a motion diagram. What's a motion diagram? One textbook that I used called them strobe diagrams. Imagine like a strobe light. So we're getting, when you watch something with only a strobe light illuminating the situation, what you get are flashes. You don't get every point in between. You just get images spaced out in time evenly. And that's exactly what we want to do here. So a child rides a bike from his house to school 100 meters away in 3 minutes. Okay. So let's do this. Let's draw axes. Because again, I need to know where my origin is. And I can draw a straight line with the help of... Oh man, that's so awesome. And let's make that go away. Let's call this the x-axis. So this is one-dimensional motion, which is what we'll stick with in Chapter 2. I think in Chapter 3 we moved to two-dimensional motion. And let's make some tick marks here. So if I can change that. Nope, that's fine. Let's make some tick marks. We're going 3 minutes at 100 meters, so I could mark every 25 meters. I can mark every 10 if I wanted. I can mark every 1, but they're going to get really close together. So let's just mark a beginning and an end. Sure. And you know what? I'm not even going to worry about... so I need somewhere... I'm just going to eyeball it. Right, so I need somewhere in the middle, and then in the middle of those. So here's x equals 0. There's 100. Let's give it units. These are meters. Sometimes you could put the meter here. Here's 50. We could give it meters. Here's 25 meters. And here's 75 meters. Okay, so this is just to label the situation. We're going to start at the origin. So here's my starting point. In fact, I bet I could make that bigger, just to make bigger dots. And we could mark every minute, right? We could mark every minute. So how far have I gone in... No, let's mark every 30 seconds. Let's mark half minutes. Because if I do minutes, I'll have... This is at t equals 0. Actually, I need that to be a lot smaller now. T equals 0 minutes. And I'm going to end up here at t equals 3 minutes. Right? And if I just mark minutes, I'm only going to get 2 data points in here. And I'd like to have a couple more than that. So how far have I gone in 30 seconds? Well, in 30 seconds, I will have gone... Well, in 60 seconds, I will have gone a third of the way, right? Which would be 33. And then... yeah, let's mark those. Why not? So 33 is about here. And 66 would be about here. So that's t equals 1 minute. And here's t equals 2 minutes. Oh, this is a motion diagram. This works. This works for us. You'll see in the solutions to this that I posted to online. I went every 30 seconds, but this works for me because this shows me an assumption that I made here. I assumed that this motion was uniform. So here, let's do this. Let's assume uniform motion. And what I mean by uniform motion is constant rate, right? Constant rate. Or constant v. All right, is that accurate? Well, if you're starting from rest and ending at rest, you have to speed up and slow down at the beginning and the end. So that's not actually accurate. But it's not a terrible approximation. And we do lots of approximating in physics, and that's okay. I approximated this child and his bike as a point. That's okay because I haven't lost any information that would affect the results that I'm looking for just yet. Okay, so let's do a couple more of these. A car travels from the grocery store to the bank 2 miles away in 10 minutes. Okay. So I could do something similar. I'm going to draw some axes. Or really an axis in this case. Make my pen a little bigger. And then make some tick marks. So there's 0. And where am I going? 2 miles. So there's 0 miles and 2 miles. There's 1 mile right in the middle. This is an x-axis and it is marked in miles. And I could mark a half mile too. Why not? Half mile and 1.5 miles. Again, let's assume that we're starting at the origin. And we're going to end up here in 10 minutes. We could mark every minute, right? So halfway through, so this is t equals, oof, it's big, let's make it a little smaller. This is t equals 0 minutes. This will be t equals 10 minutes. Now if I mark every minute, then halfway is 5. And we're going to cross, so from 0 to 5, we're not going to hit the half mile on an even minute, right? It's going to be 2.5 minutes. So I'm going to do like this and this. So 1, 2, 3, 4, 5 minutes, yeah, 6, 7, 8, 9. I should maybe mark all of these, but again, the image would get cumbersome. But what I want to point out here is, again, we have assumed uniform motion, which is okay. As long as we're aware that that we've made that assumption, that's super helpful. 5. Let me label this. See the rest of these. Perfect. And you see that the points are evenly spaced. Okay. All right. That's pretty simple. Let's do one more. A student walks to class. She starts by walking at a medium pace for 180 meters in 3 minutes. Then she reaches a hill and slows down, walking 60 meters in 3 minutes. Then going downhill, she speeds up, going 300 meters in 3 minutes. So we've got these 3 distinct sections. So let's make our axes again. That's too big. Okay. And ultimately, we're going from 0 meters to, well, let's add it up, right? We've got 180 meters in 3 minutes, and then 60 minutes meters in 3 minutes, and then 300 meters. So 180 plus 60 plus 300, what is that? That's 3, 4, 5, 540, I think. Yeah, 540. So that's 600 meters total. And that defines my scale. Let's make that go away. There. That defines my scale. You see the procedure here? Here's x in meters. And maybe just to make things nice, we'll do 100 meters. And oops, that can't be right. It's got to be 2, 4, and 6. So there's 200 meters, 400 meters. Great. Okay, and we're doing this in segments. We're still going to assume that each segment is uniform, but clearly each segment is 3 minutes, and so she's going different speeds in each segment. So from 0 to 200 meters, 0 to 180, really, that's in her 3 minutes. So she starts at the origin. She's going to end up at 180. That's about here. And let's go every minute. So here's t equals 0. At t equals 1, she's here. 2, she's here. And here's 3 minutes. There. And then in the second 3 minutes, she goes 60 meters. So 60 meters from there, right? 180 meters plus another 60 meters. She's going to end up at 240. And halfway here is 300. So 240 is like right. That's 300. Yeah. So 240 is like right here. Man, so she's and slow way down. That's fine. My data points are a little too big. So there's 3, 4, 5, and 6. And now in the next 3 minutes, she goes 100 meters each minute, right? So from 240 to 340. 340 is going to be like right here, to 440. So there's 240, 340, 440. Oh, darn. Come on now. There we go. There's 7. 2, 4, 6. I think this last bit is a little too small. Yeah, the last bit was just a little too small. And let's, just for reference, give ourselves these other, so there's 0, 1, 2, 3, 4, 5. Yeah, okay. This helps to give some reference. There's 8 and 9 minutes. Great. Okay, so again, I see 3 distinct sections. I see a moderately paced section, a slow section, and a fast section. So we will talk soon about calculating speeds for those. It's very straightforward, but I want to make a distinction between instantaneous speed and average speed.